So welcome to the keynote of the 15th IEEE International Conference Service-Oriented System Engineering. It's my pleasure to introduce our SOSE keynote, Cesare Pautasso. Cesare is a full professor at the Software Institute of the University of Lugano in Switzerland. The institute was founded in July 2017 and covers all facets of software engineering research and offers a master program in software and data engineering. At the Software Institute, Cesare Pautasso leads the Architecture, Design, and Web Information System Engineering Research Group. And his most recent research includes the BPMN sketch miner, using process mining to rapidly sketch BPMN diagrams based on user stories, RESTalk, a visual notation for modeling conversation with RESTful APIs, and Liquid software, which can roam across different edge and cloud devices. He has been working on service engineering since his PhD at ETH Zurich in 2004 with the J-Opera visual composition language, applying business process modeling to service composition and eventually making it possible to use natural language to build what at the time were called web mashups. He has co-authored a book on SOA with REST and is currently working on a new book on microservice API patterns. We will hear now about his ongoing project on API analytics and visualization. And without further delay, I give the floor to Professor Cesare Pautasso. Thank you, Cesare.
You have to unmute, Cesare.
Yes.
Yes, thank you very much to Luca for your kind introduction and for inviting me to open this wonderful conference. And I hope you can see my screen as well, because this is going to be a visual presentation. And in case you're familiar with APIs, I hope you will learn that there are so many interesting examples out there now after more than 20 years of web services and web APIs research and innovation. And after all of this time, I thought that it would be interesting to take a look at what is out there and how does it look like. So we have a new project ongoing on the API analytics, where we want to study, do some static analysis over these APIs to learn how developers design them and how can we promote best practices. And the first step was to gather a collection of real-world APIs mined from open source repositories like GitHub. And to look at this collection, we have been trying to visualize it. So if you know something about APIs, you can find lots of interesting examples. I hope you can learn something from this. And if you do not know anything about APIs, I also accepted this keynote invitation right before I was leaving for my summer holidays. And this summer, I happened to be driving a hybrid car. And the first time I ran out of gas, I opened the door and I found this plug. Then, of course, luckily on the other side, I had the usual gas, that I could fill it up and continue driving. But I was rather curious on how this works. And so the next time I found a charging station, I tried to plug in the cable, and unfortunately, the cable looked like this. And the API of the car did not fit with the expectations of the other side, and there was a mismatch. And this is something that happened in software APIs all the time. Now, after a little bit of research, I discovered that there actually, despite the fact that the EV and hybrid cars are a relatively young industry, there is already enough time to develop various types of connectors and also doing various iterations over them. As you can see, the plug over here is actually a subset of this other plug, and the reason is very simple. They needed extra connectors to support fast charging, and this part was not powerful enough. So they just took what we also do in software all the time. They just extended the API with additional connectors. Now, unfortunately, there hasn't been enough time for this to mature and reach a certain standardization, which is a pity because of the importance of the transition from internal combustion to electrical, battery driven cars. And there is a big competition in the market to see which plug is going to take over. But this makes it a pain. Of course, if you just want to drive around across different countries, and you always run the risk of ending up in a charging station that is not compatible. Now, compatibility, even if this physical connection problem will be solved, this is not the only issue. Now, when you want to charge your car, it's not enough that you plug it into the charging station, but you have to get a network ID card, and that is going to identify you, and of course take care of billing, right? Because of course you have to pay for the electricity. Now, this ID card requires a registration. So before you can charge a car, you have to register. And of course, there are so many networks in many different countries. So you have to register. Then they ask you to, of course, install an app. And then you have to, of course, enter the credit card details. And after you do that, finally, you have to wait. And finally receive the network ID card. Now, if you're already traveling on vacation, forget about doing that, right? Because you're not gonna receive this smart card that allows you to activate the charging station. And of course, there are so many networks, and it's kind of impractical to register for all of them. Now, when you go to the traditional, diesel pump, then all you need to do is just scan your credit card, fill up the tank, and the fact that you want to, maybe there is an option to actually, scan your customer loyalty card, and this is just optional, right? So that you can also just use a credit card without any additional identification. Now, for some reason, when you go the electric route, you have to, first of all, identify yourself, and then you can actually access the charging service. So this is similar what we do in APIs, where we have APIs that require to register for an API key before you have to actually, you're allowed to actually make use of the API. And this, of course, leaves the API provider in control of who is allowed to use the API. So it's important to do that, but it's also more expensive, and it requires one extra step for developers and users of the applications built on top of the API to be able to work with the service. So I will be, I was actually disappointed that to be able to charge the battery of my hybrid car, that I would have to go through so many hoops to be able to do that. And then I would actually to repeat this process for every different network in every different country that I would visit. So let's now switch to the main domain of today's topic, which is about software architectures, APIs, microservices, and I think this picture summarizes what I'm going to talk about, where we have the monolithic software that is decomposed into smaller parts so that these smaller parts can actually run in the cloud. Now, every software component has an interface. So here we have a little visualization of how a software component could look like. Now, the interface cannot be understood unless we put this component in a relationship with another component. And then we can say, well, there is the provider and a consumer. So one component depends on the other one. And the interface defines all of the shared vocabulary and all of the share interactions that are possible between the two components. If you change the internals of the components, the other side is not affected. But if you change the interface, then you will propagate the impact of the change on the other side. So interfaces are a very old concept related to information hiding and abstraction, encapsulation. And this is something that has been going on in software and programming languages for a very long time. Now, when it comes to more complex systems that are built with multiple components, then we talk about architectures. Then we can say that if a component has an interface, then architectures have an API. So how do we find the API of an architecture? Well, we have to define a boundary for the system. And then at this boundary that separates the parts of the system that we control from the rest of the software out there in the world that wants to interact with us, this is the API that connects the two sides together. So the API of an architecture is very important because it defines how do we connect together software that is outside from the software that is inside. And by inside, I mean that we sort of own it and control it, and we can switch it on and switch it off. And we are responsible for building it from the perspective of the provider. And the software that is outside is actually outside of our control and is built by somebody else. And it's supposed to connect to our system. So this is a very challenging element in the architecture to design, because you have to at the same time bring two things together that a lot, like the power charging plugs may not fit together at all, but you have to connect it somehow. And at the same time, you want to keep our system as separate as possible from the other one so that they can keep being independent from each other. So in other words, you use the API as a solution to the coupling problem. And depending on the type of API that you use, you're going to have different coupling properties. Now, usually the first use case for the API is that you have some application on the outside that needs to interact with the service provided from the inside. But the second most interesting use case is when you have multiple applications on the outside that interact through the API and share some information with each other. For example, you have Airbnb as an API allows to connect the people that are looking for an apartment and the people that offer the apartment, right? So they both connect to the API, and one provides information about their availability, and the one finds a matching place to rent. So now API actually was invented before services. This is actually goes back to classical operating systems and applications that are developed for a certain platform. And this was my first personal experience of an API when I bought this 500-page book just to learn how to write a Windows application back in the day. I don't think they are printing now these API specifications anymore, but that was very interesting to learn. Then we have also applications themselves become components and services that are reusable and are supposed to be integrated. So that's another another use case scenarios for APIs. And there was a point in which, for some reason, the industry switched from calling those web services, and they started to talk about web APIs. And of course, APIs are critical to be able to build mashups. This is also something that, for some reason, has completely disappeared nowadays. But there was a point in the history of the field in which people were building these on-the-fly situational applications in which you would just rearrange together very quickly different combinations. For example, Google Maps and then some data source, and then you would visualize the location of different elements on the map. And Well, nowadays, maybe people are actually using APIs with these low-code type of environments. Yeah? So even though you write very little code, you can do that because all of the power is hidden inside the components, and you can reassemble them through the API. So APIs are not going away; they're just becoming more and more abstract and more easy to use. So when it comes to the technology for APIs, we already seen the difference between local and remote, right? You have a co-located provider and consumer, or you have a distributed deployment where the provider is in the cloud and the consumer is in a mobile device, for example. Some APIs technology are programming language specific, and others are programming language independent. This was the very big jump ahead when it came to the first wave of web service standardization. You could make code written in different programming languages talk together, and that was actually quite challenging to achieve that. And one of the solutions to do that was actually on the somehow assumption that all of the data that will be transferred will be represented using XML. Nowadays, I don't know if people are still teaching XML, but this has been replaced by a more lightweight representation called the JavaScript object notation. And this was a very interesting example of the evolution of this technology, which the needs of the client, especially the needs of clients that would run in a web browser, were taken over, and then the providers had to adapt and provide access using a more convenient format. And of course, APIs need to be described. So you have to be able to specify what the API does so that people can discover it, they can select it, and they can actually write some code against it. So what we are going to do today is explore APIs that are remote, that they are independent programming languages, they're based on JSON, and they have a formal description, which is using the OpenAPI notation. So what I'm going to do is to walk around the beach and show you what I find. So we have gathered a collection from GitHub of these specifications, and then we are going to show you how they look like. And I hope you enjoy the process. Now, if you do not know about this OpenAPI language for specifying API, it's very simple. It's a YAML syntax in which you describe the structure of the API. And what we do is extract the paths, which represent the resources that are available. And we are just going to, also attached to the paths, we have the methods that can be applied to that path. And we are just going to build a visualization like that one. So if you, depending on the structure of the resources, the shape of the visualization is going to change, and then we can see what are the methods that we can apply. So the simplest API that you can specify with this notation that is based on HTTP, of course, is this one, right? You have one resource and one method, so there is only one operation. You can read the content of this hello. There is already a useful API that, for example, can translate some text into Braille, and you can actually retrieve the representation with an image, with HTML, or also with the Unicode encoding. And there is an API that will do that for you. Yeah? So this is an example of a read-only API that can, given a simple string as input, it will return the output in different formats, which is also another very important principle of RESTful APIs, which give you the interoperability that you need because you can negotiate between different formats. Another feature of these language is that you can have parameters. Yeah? So you can say part of the resource identifier is fixed. So here I can get the list of customers if I go here. So this gives you the list of customers, and then I have the IDs of the customers, and I'm going to retrieve individual customers. And I cannot do anything else. I cannot change the content. I can just read each customers or all of them. So we call it a read-only collection. And then this is a more complex structure that has the similar features that we've seen so far. So all of these primitives, of course, can be combined together into larger structures. This one is the even larger one. Yeah. So and what is special about this one is the fact that you have different resources, for example, contacts, customers, profiles, and then they all can be searched. And then you can express the search using a certain query. You can also add a sort criteria. So it's sort of a little query language for extracting information from the provider. This one is applied to the financial stock market. So here we have the key concept is the stock symbol, and then once you have a symbol, you can project many different types of information out of it. You can also, of course, have a symbol directory, so you can discover what are the symbols that are there, and then there is a little bit more stuff. But this is still a read-only API, so you can just extract information from it. This one is a read-only API that has just a list of things that you can get. So there is no structure, it's just enumeration of things. And then we start to find the first interaction operation so that we can actually initialize the configuration of this particular service by doing a post request. And so we call it a Retry API. And then this is a little bit more complicated, but it follows the similar. So when you design this, you have to decide, do you want to for example, here it's very clear, right? Do you want to use get then because you want to check the license, or do you want to use post because you want to upgrade? So you want to make a change to the state of the service. Here we have a third method. So in this case, we have a very small structure in which we can actually delete the user accounts. This is just a fragment that we found, and it was interesting to show this case. But before we add more complexity, let me show you another example in which the post methods are actually taking over. And in this case, we are using post, which is supposed to be something that changes the state of the service to actually read information. Yeah? So this sort of supposed to be like an anti-pattern where you say, what do? You want to get tokens, but you're actually using post to read them out. There is only one of these paths which is using get, which is a head check for some reason. Yeah, all the rest is actually doing post. And this is what I call a remote procedure call API. So you're using HTTP, but you just want to call and do something on the other side. You don't really care about using HTTP correctly, although you use the URL to distinguish which operation, which path you want to, which function, what is the name of the function that you want to call. Mapping the actions to the verbs is actually one of the most challenging things that designers need to learn. Because of course, HTTP was designed with the semantics, that is, how do we build the web? How do we build hypermediate applications where we can read the content of a website, where we can post information into it and delete pages and update them and so on. But when we have an API, we actually want to do much more than that. We want to be able to do arbitrary actions on something that is provided by the service. So here you can see an example of this designer has been trying to map actions that change the state to actions that are read-only. And what is interesting is that every action has different verb, and there is no multiple verbs attached to each of these actions. In this case, we see a little bit more structure, and it's also, see, for example, we introduce the put method, right? So for example, if you forget the password, use post, but if you want to reset it, you use put. And then there is, of course, this is a bit redundant, right? You want to delete a bookmark, you use delete, and you want to add one, you use post. Well, you could have simply attached the methods to the bookmark, and the semantics would already been clear from that. So this is if you never design one API, this is an important problem. Right? You want to express what the client can do, and then you have to squeeze these infinite number of actions into these 4 or 5, 6 HTTP verbs. Here we start to see examples of more complex trees, so they have a bit more structure. So we have the top level elements, and then we have sub levels. This one gets deeper and deeper. So we have a lot of nesting in this API. And then I wanted also to introduce this fragment that is one of the most common ones, actually, that is used to manage a collection of items. So in this case, the API has user profiles, and it gives you the possibility to create users, to manage them. And one way that we use to model how the clients can actually use this structure is with RESTOC, which is a language to specify conversations that are sequences of interactions with the API. So in this case, given this structure, one way to work with it is that you start with a container, a resource, and you say, give me the users that you have. And then in this case, there is nothing. So you create a user with post. And then what is interesting is that the response of the post request is going to contain the link, the resource identifier for the newly created user. And that is this part. Once you have that link, you can interact with it. And in this particular API, you can, of course, read the content, you can update the content, and you can repeat this multiple times, or eventually you can delete it, and then that's it. You cannot do anything else. So given the structure, it's not necessarily clear what is the behavior that is acceptable for a client, and we have a annotation to be able to specify that. More complicated structure. So this supports not just create, read, update, and delete, but also supports patch, which you can sort of say this is used to modify, incrementally modify the information associated with a certain employee. And this is actually used, for example, in this API that has a super regular structure. We, of course, find APIs that are mixing these primitive type of collection. So this is an example. And depending on the type of data, you will find, for example, here something that is read-only, something that allows you to do exactly what we've seen before with the forms, invoices, and so on. And then I think there is also this case here, which is kind of an exception in which we can only read, but we cannot create the files for some reason. Okay, so building upon that, in this example, we see that once we have an item in a certain collection, so once we have a project, and we have a certain project, then in addition to doing these basic operations that allows us to work with the life cycle of this resource, we can also perform some arbitrary commands on those. And to express them in this particular API, they have used this sort of unusual notation in which they sort of say, we have the project ID, and then we want to do something on that project ID, and then we do post. So they consistently use post to do those actions, but I suppose that maybe they shouldn't, because in this case, for example, they want to read something and they want to write something, and they use post for both. In this case, we find a more complex structure in which all of the methods are used here and there. So if you wonder if there is an API which makes full use of all the expressive power of HTTP, this would be an example. I think this is from some kind of some cloud API which allows you to work with clusters and doing backups and working with volumes, so some kind of a storage API. And what is also interesting is that they use the version 1 as a prefix. Yeah, so everything is under version 1, and then they leave space for future extension by prefixing the resources with a different version. It gets even better, right? So in this case, we have an example in which all the 5 HTTP methods are used, and this is a more complex combination of what we have seen so far. This is a similar structure in which we are not using post for actions, but we are using put for actually configuring and updating specific parts of the resources. And in this one, it's not so common actually, but it doesn't use post at all. Yeah, so in this case, we just use these methods that happen to be idempotent. So in terms of reliability, interacting with this API, it's more reliable. I also wanted to show some strange examples. So, for example, this is we still not totally sure of what does it mean to have a hashtag before the resource name, but there is a convention actually that is quite frequent in which they just make a list of procedures and then you can use post to call them, and this is somehow related to some kind of a NoSQL storage API. This one is the classical CRUD, you know, from a textbook. You know, you take a set of tables in the database and then just map them out onto the API. So you shouldn't necessarily do that, but you can really see orders, products, and then there is order products, which is like the table, you know, the join table linking the other two. And then, of course, if you really don't have time and you just want to share some data with your users, just give them an endpoint that looks like this one. You send the SQL, the API takes it, you run it in the database and send back the result. Maybe we don't really need an API. We just need an API for the database. Okay, so this concludes the first part of the talk, where I showed you individual examples to show you, become familiar with this visual notation for representing the structure of the APIs. And now, I think I still have enough time to present you some examples of how these APIs are changing over the years. And of course, I could not avoid showing you this picture, right? And if you wouldn't know anything about this particular example, you know, would you imagine that the evolution direction goes from the bottom to the top, or from the top to the bottom? In which direction are we actually improving the API? In which direction are we making it worse? Yeah? Of course, this also shows you the tension that API designers have all the time, right? Do we want to keep the API simple, or how complex should it be? And this also should make you think about the power imbalance between the providers and the consumers. If you have a provider, the provider is the side that makes the ultimate decision about what to include in the API, and the consumers just have to live with it. Of course, if you have, and this is true even if you have millions of consumers that depend on you, you can simply put up a website that says, we are going to discontinue this API next year. You have a nice countdown, and the millions of developers that depend on your API have 1 year to adopt and you know, make sure that they don't break their clients. I'm really looking forward to the next iteration of this particular API to see if finally we get some decent connections back or into these interfaces. So the challenge of visualizing evolution is related to the fact that now we have complex artifacts that change over time, and we have different snapshots of them. So we are capturing these snapshots at every commit. So every time a developer pushes a change to the API specification, we can see that. We can see when the commit was done. And this is you know, an overview of the APIs in our collection that have more than 10 commits. So if they have less than 10, we ignore them because they're not changing. The history is not long enough. And what you can see here horizontally, of course, is the APIs. So each API is basically, yeah, we have about, I think it's 260 something APIs that we filtered. And vertically, we see when the commit was done. So we see the time dimension. Yeah. So we start from day 0. This is the first commit. And then some APIs have commits that like more than 5 years later. Yeah. So this is sort of a reasonable range. Could be longer, but given the technology, OpenAPI is relatively new. There's not much, you know, we cannot go really back more than 5 years, I think, because the language didn't exist yet. But we are tracking this continuously, and you know, as time passes, we have more commits in our data set. Some APIs have more than 250 commits, so we have quite a lot of data points over here, although over a shorter amount of time. And other APIs, they only have 10 commits over a longer period of time. So I don't have time to show you the history of 250 APIs, but I have selected a few examples, and I try to visualize this history in a compact way, so we can try to observe how did the API change over time, which are the features of the API that are stable. Are there some APIs that implement what we call the this pattern in which we promise that everything will be there forever? Or are there some APIs in which parts of the API simply disappear? And those are dangerous because, of course, when you remove something from an API, the clients are going to break. So to visualize this, I'm going to show you various experiments. So what we start from is the same structures that we've seen so far, but I will plot them with this layout, and I will explain why later. But this is not just the structure of one version of the API. This is the structure of all the APIs from the history. I don't know if it's easy to see, but over here, these branches are actually no longer present in the latest version. Yeah? So basically, we see the latest version, but also we include things that were present in previous commits. Now, what we can also do is for every commit, for every branch, count how many commits it was present. So we can try to see how long or what is the age of the particular branch. So if we do that, then we can see that these very thick branches, these very big methods here are very old, and they had enough time to grow. While, for example, over here, we have a branch that was just added in the last commit. So it's still there, but it's been there for a very short time. So it hasn't had time to stabilize. Over here, we can also see these branch that disappeared. So they're not there in the last version, but they were actually never there for a long time because the thickness of the branch indicates that, this one probably was only one commit, this one a couple, and this one 5 or 6. So, and after that, they disappeared. So they were not really, it's given the fact that they were present for a short time, the impact of the disappearance on the clients is actually limited. Okay, so this is one example, and then we can do this for a couple more. And we have seen these already in the previews. So this is an example of a read-write API in which we only have get and post. And what we can see, especially I think is more visible here, is the amount of cuts that have been done to this API. What is also interesting is this example of actually changing the methods. Yeah, so we used to have a get, and then we actually have introduced a post for some reason. Yeah. This one is a read-only API, so it's one of the first examples that I've shown. And also in this case, we see how strong are some of the branches. So they have been there for a long time, and I don't know if I would trust this branch to survive that long, given the fact that others were actually removed earlier on. Does this visualization scale to more complex APIs? So in this case, it becomes difficult to read what the branches are about. But one thing is clear. In this case, we have an API that is never cutting off any branch. So it's always growing, always extending itself, but it's never removing access to existing features. So that is also an interesting case. This one is definitely an API that has removed a lot of structure, and it's also very deep. You can see here a path that has lots of nesting. And also in terms of stability, there seems to be the things that are present are relatively old, apart from a few new extensions. This is an example in which I don't know if it's very small, but you don't have to look at the beamer to be able to read this. But you see at the root, there is version 1 and version 2. So it's an example of having two different versions. At some point, they were present in the API at the same time. And then more recently, version 2 has taken over and version 1 has disappeared. So an example of a two in production type of API. This one is a bit smaller. And yeah, I think the visualization, I included it because the visualization is not so messy as the previous ones. And then this one is about the storage, virtual storage management or open storage. And we can see here the number of paths that were actually cut is much smaller. So this and actually this is quite a long-lived API. So there has been a lot of changes that we have processed. And yeah, this is also one in which the majority of the branches have disappeared. So this is a relatively dangerous API to work with, because in the past it was so much different than what it is in the current version. And finally, this one is an example in which, apart from the evolution profile, we can also see that it used only 3 different types of methods. Okay, so this is the first attempt that we used to show how these evolution of these structures have occurred over time. I think what this visualization is good is to show the stability of different parts relatively to others. So we can see which are the strongest branches of the API structure and which are the branches that have been pruned or they have been dying off over time. However, it doesn't show much about the dynamics of how these changes have happened over time, because we see whether things are there for a long time or for a short time, but we don't see when they have been introduced. So to show that, we use a different metaphor, which is the one about the 3D rings. So in this case, you know how to interpret this, right? The oldest part of the tree is at the center, and the tree grows around. Every year you can see how much it has been growing. So some years of drought, the tree doesn't grow much, and other years it grows very fast. So you can spot that. So we can take advantage of that. And then you can also see all these streaks stretching out radially from the center, and we can also try to take advantage of those to show how some features of the API have changed. So in this case, I'm just going to give you a brief tour, and then you can try to see this from an aesthetic point of view, or maybe there's also some more technical, deeper information that you can get out of this. So this is how the visualization would look like for example, the spare money API that we've seen before. So again, going from the center outside, this is representing 45 commits over a bit more than 1 month, and there are 27 paths around the tree. So this is the number of paths, and then basically the idea is that every line that you see represents the operation. So and we show the color based on the HTTP method. So in this case, this is one of these read-write APIs. It's rather small and it's only 5 days old, but there has been 16 commits. And if the line is present on the outer ring, then this is the latest version. And then we can see in the inner circle, this is how the API started. So it was much smaller at the beginning, and then more things have been added around the tree. Although this part here shows you that something has been also removed. And we can sort of see when this happens. Now, if we add more colors on the same line, it means that this is a path that has multiple operations. So in this case, we can see the post and get structure for creating and enumerating the content. And here we can see the delete, put, and get for interacting with the items. We can also see that adding multiple operations to the path is sometimes you don't do it all at once. Yeah. So, and sometimes there is some uncertainty, so you add an operation, then you remove it. Okay, this one I have explained. So all the structure is at the center. So in this case, we have an API that started with 3 different paths, with get, post, and delete. And then at some point, these paths were gone, and they replace it with a much more complex structure. This is the one that we've seen before. There was a read-write API, and this is the place in which we can see that the method was changing from a get to a post. So we can see that this happens sort of halfway through the life cycle. Now, one question is, how do we show the duration of the lifetime, right? Because I can tell you this is just 1 month of age, 95 commits, so lots of activity in a short time. But we use the rings around the center to show you actually time. So in this case, every 6 months, we draw a ring. So in this case, we have the inner circle is the beginning, and then we have 6 months, we have 1 year, and this API is actually 1 year, 2 months, and 16 days with more than 100 commits over this time. This one has lots of rings outside. So this means that it is old. It's actually 3.5 years old. But most of the activity to change it happened during the first 6 months. And this you can see at the center, right? The first ring is really big. So there's been lots of growth, lots of changes, and then it's sort of stable. There has been updates, but only a few over the last 2 years. In this case, we can see another interesting feature, which is the fact that this is actually 2 APIs into one, because historically, at the center of the circle, we can see a certain structure, and then this completely disappeared and is replaced by a separate one. And this happened even if the API is less than 1 year old. There's actually 11 months, 36 commits, and there was already a complete different change. This is one that shows you that the same happened actually 3 different times. So we start from the very early structure, and then there was more things added onto it, and then everything disappeared. It was replaced by these other parts, and then we have the most recent version that has also been growing incrementally. Sometimes this is caused by a rename in the root. For example, if you have a prefix that says version 1 and then you have version 2, then of course everything disappears under it, and you have a new version outside. This is the example of the collection, CRUD style API. So we have some collections are very old, and that's the same pattern is applied consistently over time. Well, only for 1 month. This one is much older, for 3 years, but they also use the same pattern. And it's also very easy to see that this is the API in which everything that has been added at some time will stay until the present. So this is one API that always grows and never cuts any feature. Couple more. So this one shows you how the designers have been experimenting with many different styles over time. You could argue that have been learning on the fly how to express their API using HTTP. This example here is also an example where we can see that only one path from the beginning has survived, the one sticking out on the right. So this was there from the first commit until the last, but more than half of the API has disappeared over the various iterations. This is the one that only used 3 methods. As you can see, for some reason, the designer decided that they never need to update anything, just create, read, and delete. And this is the one that actually was born as an RPC style. So it's difficult to see in the center, but this is only yellow. So they only used post. And then eventually they learned that there is this maturity model in which you start with one resource and one method, then you add more methods, you add more resources, and then eventually you add hypermedia and you reach the full glory of REST. So this is an example of such a path of the evolution of this particular API that is slightly less than 3 years. Okay, so these are 15 examples. We have published 50 in total, and there is hundreds of those to look at in our collection. You can really tell that these APIs, although HTTP is a rather constrained protocol. They really change, they really grow and evolve in very different ways. Okay, so I'm getting close to the ending time of my presentation. So I just wanted to reflect about the complex relationship between software architecture and APIs and the web. The web is great because it gives us universal connectivity where we can access software through firewalls and gives us a standard protocol to exchange data and also express, what do we want to do with the service. Everybody understands what is a get and what is a delete and what is a post. However, in the early days of web services, the web was used as a tunnel. So you were just posting SOAP messages through firewalls, and the actual knowledge about what you wanted to do was buried inside an XML document. Then there was this movement to bring back the web, there was these wars between SOAP and REST, in which eventually REST prevailed. However, there was always this problem of figuring out what REST means and designing. Every time somebody would design an API, they would claim to be RESTful, and that would be, this claim would be difficult to support. So it's always possible to find some misinterpretation of what REST is, and APIs were never RESTful enough, especially concerning the hypermedia aspect. And what about today? Well, today we are seeing more and more applications being streamed into the browser. So thanks to the HTML5 APIs and the JavaScript becoming more and more powerful in the browser, now basically entire applications are just running in a web browser from the cloud. And do you really need to talk about APIs when this is happening? This is probably worthy of further reflection of where this is going. Now, what I've presented you is a very short look into a complex landscape in which we have a sea of clients that interact with APIs. APIs evolve because of the clients, and the same way that these rocks, of course, change because of the waves. Of course, they don't change from 1 minute to the next. It takes ages. And, the critical spot in a software architecture is the point of contact. This is where change hurts, and this is where we can try to hide the ugliness of what is inside our systems and provide a beautiful representation out to the rest of the world. And this is what I've tried to do with this visualization, show you that there is something at least aesthetically interesting at the boundary. And I hope that people have been reacting to this by saying that it's very simple, but thanks to the simplicity of the visualization, you can get some insights and can learn something from this example of how to do it or how not to do it. And I would like to thank my students, my group, and also my colleagues that have been together on this journey for many years to look at APIs and try to extract design patterns from them. And I think this concludes the talk. If you want to see more examples, here are the two books that are there where you find, I think it's 100 examples over here, and this is 50 APIs with lots of visualization about their history. And these are some of the papers on which this presentation is based. So thank you very much for your attention. And I would like to hand it back to Lupe.
Thank you. Thank you, Cesare. I would like to ask you a question before, in the meantime, other people of the audience can raise hands. As far as I remember, at the beginning of the REST APIs, when SOAP was also there with a lot of importance, we described barely described the APIs, the REST APIs with the WSDL, after that with the WADL. Fortunately, Swagger appears, and now we have this more complete open API notation. Do you think that how far is the open API notation being used by the people building APIs, REST APIs in the industry? And do you think that it's going to stay, or it will be replaced soon by another specification?
Well, I think that in the short term, it's going to stay, and he's finding in our crawler, we roughly find twice as many specification every year, right? So it's like doubling every year for the past 5-6 years. So it's definitely making a major impact. And I think this is because the initial use case was to specify human readable documentation. So they would generate documentation web pages from the model that you would record using this YAML notation that I've shown. And that was a very, very important use case that would make it more efficient to provide documentation that would also be interactive, right? That thanks to the model, you can have examples that you can interact with, and that makes the developer experience they want to learn how to use the API more usable. So I think this was, as opposed to WSDL, that was more used for code generation, and you would sort of have to import the WSDL into your development environment, and then you just have some objects that represent the WSDL. In this case, the story that is behind the technology is slightly different. So I think it's here to stay and it's growing. My personal limitation, the problem that I have with it is that it doesn't support hypermedia very well. And so, you know, saying that you use OpenAPI to specify a RESTful API, well, you do it, but only without including the links, the dynamic links that you can discover interacting with the API. Now, in the long term, you know, we've been around since Corba IDL, right? So these technologies have a tendency to change. So I cannot promise anything for the next 20 years.
Okay, thank you.
Thank you for the question.
I see a couple hands. Guido, please.
Okay, first of all, Cesare, many thanks for your really interesting talk. I have two questions. One is, you already mentioned things tend to change. If you look at something like Google RPC and you have protobufs, and then you are, at least if you're old enough, you're remembered back to Corba and things like that. That's one, and I think one of the reasons for these developments is the problem with REST is, and we see it also with our students, you already mentioned it, the question how to implement, how to choose the right HTTP verb for the different operations. First, you start with everything with post, and that makes no sense, and then you want to go to hate OS and so on. But I think it's really hard to grasp the mapping between these two, because on the one hand you have a lot of features, on the other hand you have 5 verbs. So any ideas from your collections how to map semantic operations to these verbs we can use to teach people to do it the right way?
Well, I think the examples that they're shown, how do you say, the verbs were really invented to implement the web. That is a very specific type of application. And then it's difficult to twist different semantics into them. They work really well if you use the API as a shared information storage among your clients, because then the clients are going to take information, publish it into the API, and then other clients can read from the API the information that is coming from other clients. So I think this fits with the life cycle of posting some data into the API and then reading it, discovering what is there, we get, and following links. So I think this is a scenario where it fits really well. Now, if you have a different scenario in which you are publishing a set of actions that you want the service to perform for you, and then you just have to send commands into the service. And then you have a whole completely different set of problems to solve. You need to make sure that these commands are idempotent, and how do you encode the parameters? And this is the classical RPC style of an API. And then, of course, HTTP is request response, so it fits already, the interaction fits with what you're trying to do, but then you don't need to, you just tunnel everything and that's it, right? So also gRPC uses HTTP in this way. You just don't see it under the hood, and they use their own standards that work really well inside Google, and they just claim that they work for the rest of the world to encode the requests, like you said, like with protobuf and so on. So the work that we have been doing is focused on OpenAPI. There are many other technologies around, and you know, we're still getting started. Let's put it that way. Also in the patterns that we are working on, you see this yellow box about responsibility. You really need to think of what kind of responsibility does this API or the API feature has. Is it an API for holding information? Is it an API for processing data? Is it there is some stateful business process activity behind it? And depending on that, you know, being aware of these different options will help you to choose the appropriate shape for the technical part.
Okay, thank you.
Thank you, Will.
Thank you for a question, very interesting. Also, Honsu.
Oh, hello. Thank you very much for the very interesting talk. And indeed, the visualization of API and their evolution looks really beautiful, and very good to have the intuition about the API structure and their evolution history. I'm wondering the intuition in the visualization, could they be incorporated with some metrics to measure the structure or the evolution history in a numerical way, which give you another way to understand the structure and the evolution to enable for machine processing of this kind of information, which I think is very important for the users, to the developers, to understand the trend, as well as to understand the another issue for the why the API evolves from research point of view, as well as from the usage point of view. That would be very interesting to see.
Yes, this is an excellent point, and thank you very much for your positive feedback. In this talk, I've chosen to keep it more on the aesthetic level, but of course we have started also to measure these artifacts. And for example, here you can see the same example that I've been visualizing, this Open Storage SDK, in which we can show over time how the size grows. Yeah, so here you can sort of see the size in terms of how many operations does it have. So it grows from a few tens to more than 100. And also what is interesting is the relationship between the commits and the versioning. Yeah, so in this case, we can see that some commits are changing the version, and the color is based on the version. And the other commits are basically not changing the versioning metadata. So this sort of is one problem when you study evolution, is what is the granularity of the change. And here we have the fastest thing that we can observe is the commit. And then sometimes, in this case, for example, there is no versioning change for the first half of the life cycle. And then they sort of discover that they can use the version field, and then they change it a lot, right? Also, we see that this API sort of is disappearing, and then it comes back after a couple of years. Yeah, so we do have that in one paper that we published recently. So it's definitely a very important direction to look at the metrics and how these evolution can be characterized quantitatively. So I totally agree with it. Thank you.
Thank you. It's fascinating. Thank you very much.
Thank you for the question. I think there are no more hands raised. I have a very last short question. I don't know if you have measured, or you have an idea of how the security might impact the evolution of the API. So recently, the security attacks are growing and growing, and so I guess that many people who develop their APIs are worrying and wondering how to make them more secure. Do you see any impact on this in this area?
That is an excellent question, and I think there are some. For example, here you see the API key as a way to give access control, but yeah, we are not at the moment. We haven't tried to extract such to detect the presence of security aspects in the APIs, but we could definitely look into that aspect and then see how the we started to worry about breaking changes, so changes that can affect the client in a negative way, but there could be changes definitely driven by increasing the security of the API, and then I think in this case the clients have to adapt. And as if you've seen, for example, with Twitter, right, with the OAuth apocalypse, at some point they switch off basic authentication in HTTP and introduce OAuth, and they basically killed all of the applications out there that would use Twitter, right, unless they got upgraded. And so that's definitely one real world example in which this has already happened, and we can try to see if this is present in other cases. So thank you for the suggestion.
Thank you. Honsu?
Thank you. I would like to ask another question, maybe more explorative rather than a question about the work you have done. You have talked about the why API evolves using the metaphor of waves and the change in the landscapes. This is a wonderful metaphor I have ever come across. Could you say a few more things more specific about what come to the waves? Maybe in terms of what the user requirements, but maybe other things also in the waves which make the API to evolve?
Yes,
the
so
question is essentially why API evolves.
Yes, this is a very difficult question to answer if you just look at the effect of the changes, because all we can observe right now is the shape of the API over time, and we can see what is changing, and so we can describe it. But to really know the reason for that, we will need to discover some additional rationale for the change that is typically, part of the architectural knowledge that is never written down or encoded in these specification languages. So in other words, we can observe the rock, but we don't see the waves of the sea. So we don't see the clients because the clients can be anywhere, and they don't push client requirements in the GitHub repository. So that would be more challenging to study, because you will need to have a complete picture on both sides and then see how one side impacts the other. So at the moment, we are just looking where we can, and we already see interesting things. But to go deeper and understand the reason for these changes, we will need additional information, and maybe it will be more interesting to do a study with a company, for example, where they are developing the API, and at the same time they develop the clients, and then they can track the origin for the changes to client requirements. And at least this should be the theory should say that the reason for changing an API will be a new requirement for the client, and the API should only include things that are actually used by the clients. So, but that may also not be true, right? So in practice, designers put in the API things just in case, and then we don't really know if clients are using them or not. because you know, also in our experience, it's easy to find static descriptions and static artifacts, but it's much more difficult to find dynamic logs of usage because they are very sensitive information, and providers like to advertise the existence of the API, but they don't really share, or at least in my experience, they are more, yeah, they keep it more for themselves, whether there is a lot of traffic and what kind of traffic they get. Yeah.
Maybe there is also the impact of a change in the technology. For example, the popularity becomes towards microservices from the monolithic architecture. Is that the kind of thing you can observe as well?
Yes, that could be the specific artifacts that we look at are how do you say, they're not classified by whether they are microservice APIs or just you know, general APIs. They just happen to be description of endpoints that talk with HTTP, and then they themselves could be part of larger structures. So we could be actually looking, since some of those are very small actually, we could be looking at that. So very small pieces, then they actually, you know, together they would describe a larger architecture. But there is also a lack of the metadata that would allow us to detect this possible combination. So at the moment on GitHub, people just push projects, and we don't see whether the projects are correlated and connected together.
Thank you.